the development of loop quantum gravity theory, or LQG, can be traced back to the late 80s and early 90s, when a number of physicists began working on the problem of reconciling quantum mechanics and general relativity. At the time, these two theories of physics appeared to be fundamentally incompatible, with quantum mechanics describing the behavior of subatomic particles and general relativity describing the behavior of large objects, such as planets and stars. One of the key figures in the development of LQG was Abhay Ashtekar, a physicist at Pennsylvania State University. In 1986, Ashtekar introduced a new set of mathematical variables, known as Ashtekar variables, which allowed general relativity to be reformulated in a way that was more amenable to quantization. This led to the development of a new approach to quantum gravity, known as canonical quantum gravity, which aimed to quantize the gravitational field using the techniques of quantum field theory. In the mid-90s, a group of physicists, including Carlo Rovelli, Smolin, and Jorge Pullin, began working on a specific variant of canonical quantum gravity that later became known as loop quantum gravity. The key idea behind LQG is that space is not continuous, but instead is made up of discrete loops or networks of interlinked lines. These loops form the building blocks of space, much like atoms form the building blocks of matter. The first major breakthrough in LQG came in 1995, when Rovelli and Smolin showed that the theory predicted a discrete spectrum of areas for two-dimensional surfaces, rather than the continuous spectrum predicted by classical physics. This was a significant result, as it demonstrated that LQG could make testable predictions about the behavior of spacetime. Over the following years, researchers continued to refine and develop LQG, exploring its implications for black holes, cosmology, and other areas of physics. In particular, LQG has been used to study the behavior of spacetime at the Planck scale, where the effects of quantum gravity are thought to become dominant. Today, LQG remains an active area of research, with many open questions and challenges still to be addressed. However, the theory has already provided important insights into the nature of space and time and continues to offer new avenues for exploring the frontiers of physics.